Hey folks, I got an example of something rolling down a hill, and we're going to use the idea of energy and the translational and rotational kinetic energies. We're also going to do a little review of dynamics from the previous chapter, and we're going to do some compare and contrast. So the situation is we have a solid disk or cylinder on a ramp, and we're starting from rest, and we're going to let it roll down the ramp, and it's going to roll some distance d down the ramp. So we're going to do everything in terms of d, okay? Oh, and the angle of the ramp from the horizontal is theta. Okay, so we're going to do everything in terms of those two things, the mass and radius of the disk. And let's back up a second here. Let's say this were just a block on a frictionless incline. So we're going back to like chapter 5, okay? And I asked you to figure out the acceleration of the block, okay? Well, the answer you would get would be A equals G sine theta, okay? So that would be the acceleration of a block on a frictionless incline, okay? Or a car with frictionless wheels moving down an incline. And if you then did some kinematics with that acceleration, you could find the final velocity. So the final velocity would be root 2g d sine of theta. Now, by the way, you can determine that final velocity either by doing dynamics and then using, getting the a and then using kinematics, v final squared equals v naught squared plus 2a delta x. Or you could use conservation of energy to get that final velocity. mgh equals 1/2 mv squared, and h would be d sine theta. That would work too. Now, that's if we have a thing that's not rolling. So that's on a frictionless incline, a mass going down the incline. Okay, well, what if we start having this? Now we go back to our situation. We have a disk rolling down the incline. How is its acceleration going to compare and its final velocity going to compare to the mass on a frictionless incline? Okay, well, we're going to figure out the velocity at the bottom of the incline, and we're going to use two different methods. One is we're going to use dynamics. Okay. And dynamics means we're going to use net force and net torque. All right. So in order to do dynamics, I got to draw an FBD of the disk. All right. So here's the disk. Now, the forces that would act on the disk are gravity, force of gravity, which is going to act at the center of the disk, or we pretend it all does. And what else? Well, you're going to have your normal force, which will be applied there where the contact point is, and that'll go through your center of mass, and that'll be force normal. And then you're going to have friction, and friction is going to point up the incline, okay? Because this point right there is trying to slide to the right, so friction is going to oppose that relative motion, and it's going to pull left. Now, the next thing we need to do is we need to break all those forces down into parallel to the motion and perpendicular. Now, by the way, at this point, it's important not only which way the forces point, but where their point of application is. So you'll notice here, I was very picky about having the normal force and friction force. That's where they're acting on the disk. And the center of mass is acting at its center, okay? All right, now, the good news is two of these forces we don't got to do anything to. Force normal is already perpendicular to the motion, and force of friction is already parallel to the motion, or anti-parallel, or whatever. Gravity is the one we got to break down. So you're going to have your mg cosine of theta, and you're going to have your mg sine of theta. Okay, so then we do net force equals ma. We're going to say down the incline is positive because that's which way the disk is going to roll. So you'd have mg sine theta minus friction equals ma. Now, the problem with that is we have two unknowns. We don't know A, and we don't know friction. And I didn't give you a coefficient of friction, and even if I did, it'd be static friction, because it's static friction because the disk is not slipping on the incline at all. So this is static friction, and you might recall that the force of friction static is less than or equal to mu SFN, and more than likely we're at the less than, because unless unless you increase that incline until the disk is just about slipping, that would be the equal. Here are probably less than. So we really don't have any information on friction. So what we have to do is use net torque equals I alpha. Now, when you do this, you have to pick an axis, okay? You have to pick which axis you're going to look at torque about. I'll pick the center of mass, okay? So what forces cause torque about the center of mass? Well, only one of them, friction. The other three forces, their lines of force pass through the center of mass. Therefore, they don't cause any torque about the center of mass. In other words, the only force making this thing spin is friction, okay? If there wasn't any friction, it would never spin. It would just slide down the incline without spinning. So the force of friction, its torque, is R cross F, so that'd be R times force of friction equals I. Now, for a disk about its center of mass, we have 1/2 mr squared. And then finally, alpha. Well, alpha is equal to the acceleration of the center of mass divided by r, okay? So I made a bunch of substitutions there. Now, here's the cool part. A lot of that stuff cancels, like this radius and one of those, this radius and this one, so the r's are all gone. And you get an expression for friction. Friction has to be 1/2 ma. And then I'm going to take that and plug that in here for friction, and we're going to get our acceleration. So you got mg sine of theta minus friction, which we now know is 1/2 ma, and this equals ma. Hey, look, the masses cancel. Surprise, surprise, right? The acceleration shouldn't depend on the mass. And you get a little algebra here. You get g sine theta equals 3/2 a, or a is 2/3 g sine theta. Okay, now compare that acceleration to our rolling cylinder to the acceleration of a frictionless block. This acceleration is only 2/3 as much, which means the disk is not going to be going as fast when it gets to the bottom of the incline. It won't be going as fast as the block sliding on frictionless incline. Okay. Now that's how you would find the acceleration using dynamics. And then how would you find the final velocity? Well, if I had the acceleration, I would just use v final squared equals v naught squared plus 2a delta x. We're trying to find v final. V naught was 0. 2, the a we just found, it was 2/3 g sine theta. And then delta x is just d, the distance we rolled. And v would be square root of all that. So if you put that in there, you get 4/3 g d sine theta. And again, compare that to the final velocity of a frictionless block on the incline. This is 2. This has a 4/3, which is less than 2, right? So our cylinder is not moving as fast as a frictionless block would, okay? So that's using dynamics, all right? Well, what if we wanted to use energy to answer these two questions? Okay, well, that's pretty easy to do, okay? And when we do this, you can decide which way you'd want to do it. They're both probably about the same effort, the same work, no pun intended. But I typically, if I have a choice, I typically use energy to answer these questions. So let's look at energy. So the disk starts with what kind of energy? Well, gravitational potential energy. At the bottom of the incline, what kind of energy does it have? Well, it's got two types of kinetic energy. It's got kinetic translational, it's moving forward, and it's got kinetic rotational, it's spinning, okay? So we say gravitational potential energy is going to turn into rotational energy plus translational energy, okay? So we've got mgh equals 1/2 I omega squared plus 1/2 mv squared. Now I want to pause here for a second. Off to the side here, what if this were a frictionless block sliding down the incline? Well, then you'd have the same mgh, right? Let's assume it's the same mass. But that would only turn into 1/2 mv squared. So all of the gravitational potential energy would go into making the block move forward. Well, here, only some of that gravitational potential energy makes the block move forward. Some of it also has to be used to make the block spin. So that's another reason why the block is, or the cylinder is not moving as fast at the bottom as a block would be, because only some of the potential energy gets to make the block move forward. Okay, we have to spend some energy making it spin as well. Okay, now as far as the math goes on this is pretty easy. You got mgh equals 1/2. The moment of inertia of a disk about its center of mass is 1/2 mr squared. Omega is v over r. If I square that, I get v squared over r squared, and then plus 1/2 mv squared. Lo and behold, the masses drop out again, right? And also the radiuses cancel. So it doesn't really matter if the radius of the disk is 1 inch or 1 meter. It'll get to the bottom at the same time, okay? And we get GH equals, you get 1/4 v squared plus 1/2 v squared. You get 3/4 v squared, or v is the square root of 4/3 GH. Okay. Oh, and I didn't give you h, but hopefully you'll look at the trig up here and you'll say, what's the height? Well, the height is just d sine theta. It's just a right triangle there. So let's make that substitution in here. So that'd be root 4/3 g d sine theta. And that's the same answer we got before for the final velocity. But this time we got the final velocity first, not the acceleration first. Okay. And then if you wanted to determine the acceleration, well, then I would go back to kinematics. V final squared would equal v naught squared plus 2a delta x. V naught 0, your final velocity is there. Delta x is just d. And guess what you're going to get for the acceleration? You would get the exact same thing we got before, which is 2/3 g sine theta. So I'll just write that down. Okay, so you'd get the same answer. So to solve a problem like this, you can look at it either way. Okay, you can use dynamics to solve it, or you can use conservation of energy to solve it. There's no preferable way to do it. You pick which way you like better. I personally prefer using energy. I just think it's a little more elegant. But neither one is correct or incorrect. So the next video, we'll talk a lot about concepts with rolling, and we'll do some more examples. So I hope this video was helpful, and thank you very much.